Hi, today I'm going to present our work on a Retinex based GAN pipeline to utilize paired and unpaired datasets for enhancing low light images. So this work is carried out by the Department of Computer Engineering, University of Peradeniya, and the Department of Electrical and Electronics Engineering, University of Peradeniya. Harshana, myself, Gihan, and Suren, Sritharan, and Professor Ragel are from the Department of Computer Engineering, and Dr. Roshan, Dr. Parakrama, Ekanayeka, and Dr. Vijitha, Herath are from the Department of Electrical and Electronics Engineering. So to begin, we have the new hot field of computer vision, where basically 2000 high quality research papers are published on the top venues every year. So these papers discuss a lot of things such as object detection, scene interpretation, annotation, summarizing, color analysis, and everything. And there are many vision-based products such as self-driving, text recognition, and even color filters for these photographs. But the issue is most of these algorithms, like 99% of these 2000 papers and all the products, work only on well-lit images when the lighting condition is really good. But when it's dark, like the image on the left, it's very difficult to get any of these things done. So our work tries to solve this problem. So existing solutions to this are like non-algorithmic and algorithmic. The non-algorithmic ones are like artificial lighting, which is basically an energy consuming method, and also it's not suitable where you can't put in light pollution. Light pollution is when you go and put a light in a nocturnal ecosystem, or else like a community or a city where people don't need that much of light. And then there are sophisticated camera hardware, which is very expensive, and there is HDR imaging, which also has a problem of the ghosting effect, which is basically the blur image of images when things are moving. So none of these non-algorithmic solutions are perfect. Then we go for the algorithmic ones. The existing work is like classical algorithms, which are classical signal processing techniques such as equalizers and gradient enhancement techniques. And then there is Retinex theory. We'll go into what Retinex theory is later, and also we'll go into what paired and unpaired data sets later. And then we have deep convolution network for enhancement of low light images, which is low light net, low light CNN, and then there is Retinex net. So our work mainly draws inspiration from Retinex net, and then there is adversarial learning based techniques where we use generative adversarial network, and our work mainly draws inspiration from this enlightened GAN paper. Moving on, what is Retinex? So the idea of Retinex is a way of understanding human vision as well as lighting condition in images. The bigger picture is that every image S is an interaction between the actual object that was there, which is the reflectance, the color information, and the illumination depth, which is the light information at the particular moment. So even the same scene on two different images can have different illumination maps based on the lighting conditions, but we hope ideally the reflectance map is the same because the objects have not changed. They reflect the same as long as you put the light. So we have this, and we need to build up a neural network to split an image into the reflectance and the illumination. For that, we use Retinex based decomposition network, where basically we try to do three things here. We optimize the network to do three things: keep the reflectance map for the low lit image and the corresponding high well lit image as close as possible. Then keep it in such a way that you can generate the original image by the reflectance and the illumination maps. Do it as much as possible. And then an intuitive idea about the illumination map is that it should be smooth, because you can't have sharp edges on the lighting distribution. The objects you can have, but the light you can't. So we put in all these three loss functions, and then we build a Retinex decomposition network based on prior work, and then we train this with a paired data set, because for this you need a well-lit image and a low-lit image. So it's based on this work from 2008, and we train a neural network to do this on patches, not full images. But here, since you have the same image as the low lit image and the well lit image, you can go for patches because the patches are also corresponding to each other. So we train this neural network on a supervised learning way. And then let's look at what these two types of data sets we are talking about. Paired data sets are basically when you have a low light image and a well lit image. And they are difficult to collect because you can't find, you have to wait like several hours to get the low lit image of the same scene. But they have more information because you have pixel wise correspondence here. Then we have unpaired datasets, which are basically a lot of well lit images and a lot of low lit images. So these things are easy to obtain, but not much informative. We need to use both these things. We use paired datasets in the decomposition. Now let's see whether we can use unpaired datasets. So for this, we use generative adversarial networks, specifically deep convolution generative adversarial networks, which is like generator and the discriminator of the GAN is CNN based. So what we are going to do is we need to find the illumination level of an image. So this is after Retinex decomposition, given R and I, not S. Given R and I, we need to find the illumination level. Then we need to extract the color information. Even in the poor light condition, then we need to increase the illumination while preserving the and enhancing the color information. And then within the process, you get a lot of noise and you need to do denoising to get a good image. So this is our motivation. Then for that, we use an idea called CycleGAN, which is basically training a GAN to take a low lit image, make it well lit, and then make it low lit again, and still it should come to the original image. So that idea is very useful when you don't have the corresponding well lit image, but still you have the original low lit image. So you can take it in a cycle and see whether it's there. So it's basically having the true values even when you don't have them. So it's a tricky thing. So we use that, and this is the complete model. And you can see for images, you have decomposition, then you enhance, then you take it back, and you try to optimize the whole cycle. So if you look at the smaller components, so in the forward pass of the cycle, you have decomposition and enhancement. So image get decomposed into illumination and reflectance, then they get enhanced. Specifically, the lighting information get enhanced, but then the color information and the enhanced lighting information goes to a well lit image. You have the de-enhancement thing, the reverse generation. That's also more or less the same, except the functions being used here to de-enhance the illumination map. So, and also we have a discriminator, which is basically going to find, given an image, whether it's an actual well lit image or an enhanced well lit image, or else whether it's an actual low lit image or a de-enhanced low lit image. So we need to build up a loss function to incorporate all these things. For example, we have loss functions for the generate as well as the discriminator, and also we have the cycle consistency loss, which comes under the generator. So cycle consistency loss also works for the complete image, the S, the image, as well as the closeness of the reflectance maps in both well lit and low lit conditions, based on the idea that it's invariant across different lighting conditions. So you can refer the paper for the specifics of this, because it's a lot of equations and we have the explanation very detailed in the paper. So please refer to that. So anyway, this is the proposed complete model. Again, the image is a little bit complicated, but it's explained very well in the paper. And here we are trying to give you a overview of what we have done. The important thing to remember is the decomposition is trained on paired datasets, while the enhancement is trained on unpaired datasets. And these are the results of the low lit images and what should be the answer with the well lit image. And we have results from a generic GAN and a generic CycleGAN, which is like the prior work. And then we have the results from our model, which is superior to the previous work. So you can see they are very close to the corresponding well lit image. So on conclusion, we have proposed a method that combines ideas from Retinex theory and CycleGAN, and we use paired and unpaired images, and we show better performance. And we have done an ablation study of inner workings of the neural networks on the paper, like what happens in different layers and whether our intuition about these different components are true, whether they work as we plan. And then we have some images showing issues, and we try to discuss these things. And also we have found out a neural network then use paired and unpaired datasets, but on two parts of the neural network, not everywhere. So one part uses paired and the other part uses unpaired. So we hope to build up a neural network where both the decomposition and enhancement uses both of these types. Then thank you very much for listening, and we are ready to take your questions. And so this is a summary of our work. Image enhancement algorithms are of two types. They are for two reasons. One is basically enhancing the images, and the other one is to improvement. So prior work is dependent on either paired or unpaired datasets, and we propose a CNN and GAN based model based on the Retinex theory of human vision, color vision, to utilize both of them. And then the proposed model performs better and gives better results compared to similar models. And we have future work which has been discussed here. So thank you, and please feel free to ask questions.